Let's continue in section 3.1. We're learning how to graph quadratic functions. We learned a new formula called vertex form. You see it in the green box. A times x minus h quantities squared plus k gives us the vertex right away at h comma k. And in the last video we learned this is true because of what we already know about transformations of the basic function x squared. So in example 2, let's just go ahead and find the vertex first, and then we'll come back and find the intercepts after that. So look at the number after the x is a positive 1. Because there's a minus sign here, we need to change the sign on the plus 1, and so the x coordinate is going to be at -1. And then the y coordinate comes right here, and because there's a plus sign right here, we're going to keep the sign of the -4. We're going to have a y coordinate of -4. If there's a vertex at -1, -4, there's an axis of symmetry. A vertical line through the vertex is the axis of symmetry, so that's x equals -1. And we can go ahead and take care of that as well. Okay, so we took care of the vertex. Let's go ahead and figure out what these intercepts are, and then we'll sketch the graph. So let's see here. Do you remember to find the y-intercept we set x equal to 0? We have g of 0 is equal to -0 plus 1 squared minus 4. If we simplify that, we get -5. And so our ordered pair is 0, -5. And for the x-intercepts, we set y equal to 0. We say negative x plus 1 squared minus 4 equals 0. And then we solve for x. So we can go ahead and add 4 to both sides. Although, you know, we want the x plus 1 squared to be positive. And so it might be better if we added x plus 1 squared to both sides. That might save us a step. Cancels over here. We have -4 equals x plus 1 squared. Or if you're used to seeing the x on the left side, you could write it as x plus 1 squared equals -4. And the interesting thing is that now when you use the square root property, you get x plus 1 equals plus or minus the square root of -4, which is not a real number. So we could go on and write the non-real complex solutions, use the number I to do that, but that won't help us with the graph. When we graph, we're only graphing real numbers. And so what we can do is we can stop right here and we can say no real solutions. And then we can say there are no x-intercepts. And that's a bit of a surprise. Maybe we should think about this question for just a minute. How many x-intercepts could a quadratic function have? So let's find a little clear space on our paper, and let's think about this question for just a minute. how many x-intercepts could a quadratic function have? Well, in the previous example, in example number 1, we had a graph that looked about like this. And so we had 2 x-intercepts. Can you see how we would get no x-intercepts? Well, if we shift this parabola up above, so that the vertex is above the x-axis, then we'd have something like this, and then there are no x-intercepts. And so this is the basic idea of the graph in example number 2. And let's see, there's actually one more possibility. Can you think of a parabola that doesn't have 2 x-intercepts and it doesn't have no x-intercepts either? How many does it have? It has exactly 1. The vertex, 1 x-intercept. And the classic example of that would be the basic function y equals x squared, right? It has exactly 1 x-intercept. And of course, here's another example I've just drawn. So anyway, let's go back to our problem now and try to finish this up. So actually, there was one more thing I wanted to talk about in this function, and that's this negative sign right here in front of the x plus 1 squared. Do you remember what it does to the graph? When we studied transformations, we learned that the negative sign in front represents a vertical reflection, a reflection over the x-axis. And so when you reflect that parabola down over the x-axis, then we say that the parabola opens down. The parabola opens down. And so this is another nice property of the parabola that we should identify. Okay, let's go ahead and make the graph now. Let's plot the y-intercept at 0, -5. Let's see here. -1, 2, 3, 4, 5. 0, -5. And the vertex at -1, -4. And that's all the points that we have. That's not very many, is it? So let's do this. Let's draw in the axis of symmetry at x equals -1. Let's put a scale on our graph. We don't have to label all the tick marks, but we should label enough so that we know what we're counting by in the x and the y directions. Let's go ahead and find the mirror image of this y-intercept over on the left side of the graph. So can you see where it would be? From the y-intercept, 1 unit over to the axis, so then 1 more unit over to its mirror image. And so there it is at -2, -5. And we could just go ahead and draw the parabola through those 3 points, although it might be even nicer if we just got 1 extra point. So let's see here. Could we do maybe I could fit it in right here. I could get an extra point by finding g of 1. And so if I plug in 1 for x, I've got negative 1 plus 1 squared minus 4. That's 2 squared is 4. Negative 4 minus 4 is negative 8. G of 1 is negative 8. It's just barely going to fit on my graph. Right down at the bottom edge, I can plot 1, negative 8. And then I can plot its mirror image on the other side at negative 3, negative 8. And now with 5 points, I feel a little better about drawing the smooth curve, the parabola, through those points. And we're done.